Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, and we're going to be talking about Taylor series and Maclaurin series. So let's go ahead and dive into it. What is a Taylor series? So here you have the definition. A Taylor series centered at some x value a is equal to, first you have f of a, right? That's where you just plug in a into the function, plus the first derivative evaluated at a times x minus a, plus now the second derivative divided by 2 factorial times x minus a squared, so on and so forth. So what does this look like as a series? Well, here we have the summation n equals 0 to infinity. You take the nth derivative, you evaluate it at x equals a, you divide by n factorial, and then you have x minus a all to the power of n. So what this is giving you is an infinitely long polynomial, right? So here we have a Taylor series centered at x equals 0 is called a Maclaurin series. So bigger world, we have the Taylor series. At specifically x equals 0, that's when we have a Maclaurin series. So we're going to go ahead and find the Maclaurin series for e to the x. I think it's one of the nicest ones to do in order to understand the process. So the first thing that you want to do when you're going to look for the Taylor series expansion is you want to take all of the derivatives. E to the x is simple, right? Because, we get f prime of x is equal to e to the x. The second derivative is equal to e to the x, right? So we're going to just keep going with that. So usually you go up to as many derivatives as you want. Sometimes it tells you to find like the first 4 terms of the series. Sometimes it just asks you to find the summation, right? Stuff like that. Depends on what you're being asked to do. We're just going to go to the third derivative today. And what we're going to do is we're going to evaluate these at our a value of 0. So we get e to the power of 0 is equal to 1. So all of these guys are equal to 1. So let's go ahead and write out the Taylor series. So first we have f of a, which is just equal to 1. That's going to be f of 0 plus the first derivative, 1, divided by 1 factorial times x minus 0 to the power of 1. Plus, now we get 1 divided by 2 factorial times x minus 0 squared, plus 1 over 3 factorial, and that's going to be x minus 0 cubed, plus so on and so forth, right? So if we were to simplify this, we get 1 plus x. That's going to just be x squared over 2 plus x cubed over 3 factorial, plus so on and so forth. So now we can go ahead and write this out as a series. We get the summation. This is going to be n equals something to infinity. So notice what we have here. We have whatever is the exponent, we're dividing by that factorial, right? Here we have the exponent of 3, and we divide by 3 factorial. So we get x to the power of n divided by n factorial. And now we can think about our index, right? We're starting at 1, so our starting index, we want it to be 0, right? X to the power of 0 divided by 0 factorial, that is equal to 1. So what we did was we found a Taylor series which represents e to the x. And actually, we can go ahead and use this to help represent other functions similar to e to the x. So here we have use the above Maclaurin series for e to the x to find the Maclaurin series for x to the power of 4, e to the x, right, and e to the negative 2x. Now that we found the series for e to the x, we can use that to manipulate things that are pretty similar to it. So let's go ahead and start with x to the power of 4 times e to the x. One way you can do this is you can just replace it with the actual series in order to write a new series for it. So here what we could do is we could plug in what this is equal to, right? We just found this is equal to this, x cubed divided by 3 factorial plus ... So we can multiply that x to the power of 4n. So x to the power of 4, that's going to be x to the power of 5 plus x to the 6 over 2 plus x to the 7 divided by 3 factorial plus blah, blah, blah. So let's go ahead and try to write this as a series. We get the summation n equals something to infinity. Now we're starting off at x to the power of 4. So we can write this as x divided by something factorial. We could either have n plus 4 divided by n factorial, right? We're just adding 4 to the exponent each time. Or what you could do is you could change what we're starting at. So here, what if we started at 4, right? At this one, the original one, we're going to start at 0, right? What if we started at 4? Then we would have x to the power of n, but then n minus 4 factorial in the denominator. And I'm sure there's other ways that you guys can write it, right? Any of these are going to be the correct answer. So that's one way you can find the Maclaurin series is you can write out the actual terms, multiply it in, manipulate it, rewrite the new series. Another way you can do it is to just replace it with the actual series. So let's go ahead and see what that looks like. x to the power 4 times the summation n equals 0 to infinity. That's going to be x to the power of n over n factorial. And now what we're doing is we're just combining these x's, right? What happens when we combine them? We add their exponents together. So we have the summation n equals 0 to infinity. That's going to be n plus 4 divided by n factorial. So you can also just straight up replace it with the series. Let's go ahead and think about e to the negative 2x. One thing we can do is replace x in our series. So this is equal to the summation n equals 0 to infinity. Instead of x to the n, we replace it with negative 2x to the n divided by n factorial, right? And if you wanted, you could split this into all of the pieces, n equals 0 to infinity, negative 1 to the n, you could pull out that 2 to the n, and x to the n, you could leave that as 2x to the n. Doesn't make much of a difference, right? That's because you're kind of just treating it like a function. So if you have e to the f of x, all you have to do is you just plug it into the summation n equals 0 to infinity. That's like plugging in f of x to the n divided by n factorial, right? You can just think of it like a function. So these are some examples of how we can use a Maclaurin series in order to represent functions as power series. Now let's go ahead and find some more Maclaurin series, right? We want to find the Maclaurin series for f of x equals cosine of x, and we want to find its interval of convergence. So let's go ahead and start off with finding the derivatives. So f of x is equal to cosine of x. Let's go and find up to the fourth derivative. So first we get negative sine of x. That's the first derivative. The second derivative is going to be negative cosine of x, right? The third derivative, 1, 2, 3, that is going to be now positive sine of x. And now our fourth derivative, this is going to be equal to back to cosine of x. So we kind of just went in a little cycle, right? Now what we want to do is we want to evaluate all of these at our a value. In this case, the a value is going to be 0. So we have cosine of 0 is equal to 1, right? At the starting value, if you think about cosine, it starts right here before it goes down. The first derivative of 0, evaluated at 0, that's negative sine of 0. That is going to be equal to 0. Sine starts up here before it goes up. Okay, so second derivative, negative cosine of 0, that's going to be negative 1. The third derivative, that's going to be sine of 0, which we know is equal to 0. And then finally, f to the power 4, the fourth derivative at 0. That's going to be cosine of 0, so we're back to 1. Okay, so now let's go ahead and evaluate all of these. First, we have f of a, so f of 0, that's just equal to 1, plus f prime, that's equal to 0 times x minus 0, plus, now we go to the second derivative, so negative 1 over 2 factorial times x minus 0 squared. Now we get 0 over 3 factorial x minus 0 cubed. And then we go on to our last derivative, so 1 over 4 factorial x minus 0 to the power of 4. So if you like those color-coded, right, we have our first f of a, right, just f of 0. Then we have the first derivative, the second derivative, the third derivative, and let's choose purple, the fourth derivative. So that's where we get all of those from, right? And then we always divide by whatever power that we're at, factorial. So here we're on the second power, we divide by 2 factorial, the 3 power, right, and the 4 power. Okay, so then plus dot, 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 because this is going to go on forever. So let's go ahead and simplify this. We get 1 plus, that second term goes to 0. So that's actually going to become minus 1/2 x squared. Then we get plus 0 plus 1 over 4 factorial x to the power of 4 plus dot, dot, dot. Notice that all of the odd terms are going to go to 0 because all of those are when sine is equal to 0, which is always going to be 0. The even terms are when we're evaluating cosine of 0, which is always 1 or negative 1, right? So here we get the summation, n equals something to infinity. Here we have even power, so I know it's going to be x to the 2n, but we always divide by that same power, factorial. Now, we also have to remember that we're alternating between positive and negative, right? So here we're going to want a negative 1 to the n. So our starting value is equal to 1, so we know our starting index is going to be at 0. So that's how we can represent cosine of x with the Maclaurin series, and this is going to be centered at x equals 0. The second part of the question, though, because since we're not done, is we want to find the interval of convergence. So if we remember how to do that, we use the ratio test. So r is equal to the limit as n approaches infinity. We take our n plus 1 term, So this is going to be negative 1 to the n plus 1, x to the 2n plus 1 divided by, and that's going to be 2 times n plus 1 factorial. Remember, we're adding 1 to n. So we have to make sure that, like, for example, where we're multiplying this by 2n, we have to multiply that 2 by the n plus 1. Now we just need to divide by the actual terms. And in order to divide, I'm just going to multiply by the reciprocal. So we multiply by the reciprocal, we get 2n factorial in the numerator divided by negative 1 to the n, x to the 2n. So let's go ahead and see what cancels out here. First of all, we have the negatives cancel out because we're working in absolute values anyways. Now let's go ahead and distribute this 2, right? Because this is going to become 2n plus 2. And notice that one of them cancels out here. We have x to the 2n cancels with x to the 2n. That just leaves an x squared in the numerator. And now let's talk about our factorials. So in the denominator, here we have 2n plus 2 factorial, which is equal to, that's going to be 2n plus 2, 2n plus 1, and then we have that 2n factorial. So that is going to be very nice because those 2n factorials are going to cancel out. So here we're left with a limit as n approaches infinity of whatever we have left over. We have an x squared in the numerator divided by 2n plus 2 times 2n plus 1. So what's going to happen to this limit? N here is going to infinity, and the only n terms we have are in the denominator. So that denominator is going to get really, really big, which means this entire limit is going to go to 0, regardless of what x is equal to. So remember, for the ratio test, we want our ratio to be less than 1. If it's less than 1, then it's going to converge. And since it's less than 1 for all x values, it doesn't matter what x value I plug in, the denominator is still going to get really, really big. Then that means this is going to converge for all x values, right? So let's try one more example here. We're just going to go ahead and find a normal Taylor series. So when it's a normal Taylor series, it just means it's not centered at 0. This one's going to be centered at x equals 8 when we're doing f of x, which is the cube root of x. So our first step is always to find the derivatives. So f of x, I'm going to rewrite as x to the power of 1/3 just so I can see the powers really well. And now we get f prime of x is equal to 1/3 times x to the negative 2/3. The second derivative is equal to, that's going to be negative 2/9 x to the negative 5/3. Just add 1 to the exponent, right? Or subtract 1. The third derivative, let's multiply. Okay, so that's going to become positive 10. 9 times 3 is 27. X to the negative 8/3. And maybe we can just go to the third one. Yeah, we want to find the first 4 non-zero terms, right? So let's go ahead and plug these in. We're going to evaluate it. F of 8 is equal to the cube root of 8, which is just equal to 2, right? 2 cubed is equal to 8. Okay, so let's go ahead and use that. Let's find the first derivative. We get 1/3 times, that's going to be the cube root of 8, which we know is equal to 2, raised to the power of negative 2. So really, this is 1/3 times 1/4, which is equal to 1/12. Second derivative evaluated at 8. We get that negative 2/9 times the cube root of 2 is, the cube root of 8 is equal to 2. And that's going to be raised to the power of negative 5. So you can think of this as negative 2/9 times 1/2 to the power of 5. Notice here that one of these 2's is going to cancel out. So it's going to be a 4. So what does that leave us with? That is equal to negative 1/9 times 1/16. So, don't be afraid to whip out old-fashioned math. We get 54, 144. So we get negative 1/144. Lots of numbers here. Okay, let's find the third derivative evaluated at 8. 10/27 times the cube root of 8, which is equal to 2, and that's going to be to the negative 8. So 10/27 times 1/2 to the power of 8. Let's go ahead and think about this. We can pull a 2 out of the denominator and the numerator, so that leaves a 5 in the numerator. 5/27 times 1/2 to the 7. This is equal to 5/3, 4, 5, 6. It's a very good number. Okay, so we did lots of math. Now we're going to go ahead and do the actual calculus part of it. The first calculus part is finding the derivatives. The second calculus part is plugging it in for the Taylor series. So the first thing we do is take just our normal function evaluated at 8, 2 plus. Now we take the first derivative evaluated at 8, so 1/12. 1/12 times x minus 8. And now we start dividing by the powers, right? So this one right here, negative 1 over 144, negative 1 over 144 times 1 over 2 factorial times x minus 8 to the power of 2, right? So this is instead of plus minus, I'm just going to make this a minus. Now we get plus, and let's see, our last one right here is 5 over 3, 4, 5, 6. So here we get 5 over 3, 4, 5, 6 times, now we're going to have 1 over 3 factorial, x minus 8 to the power of 3 plus dot, dot, dot. This one, I'm not going to even write it as a series. I'm just going to leave it as is. All it wanted us to do was find the first 4 non-zero terms, which we did right here. The less math you have to do saves you from errors. I might make an error later on if I'm multiplying these all together. So that is exactly how I would leave it. But that's all I have for us today on Taylor Series and Maclaurin Series. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other topics you'd like to see done. Thanks for watching.